Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like parallel computers, shared memory computers, distributed memory computers, hybrid systems, network computers. Let's get started. Slide 1. Introduction to parallel computers. Parallel computers are designed to execute multiple tasks simultaneously by distributing workloads across multiple processing units. This makes them far more efficient for complex calculations than traditional single-core systems. Explanation of parallelism. There are different ways parallel computing is implemented. 1. Bit-level parallelism. Instead of processing one bit at a time, the processor handles multiple bits in a single operation, improving speed. 2. Instruction-level parallelism, ILP. The processor executes multiple instructions at once rather than waiting for one to finish before starting the next. 3. Data parallelism. The same operation is applied to multiple data points, such as adding two large arrays element-wise. 4. Task parallelism. Different tasks run in parallel, like different modules of an application executing at the same time. Example: IBM's Summit supercomputer, one of the fastest computers in the world, uses parallel processing to run climate simulations and AI computations. Significance: parallel computing is vital for AI, scientific simulations, gaming, and data-intensive applications. It helps solve large-scale problems efficiently, reducing execution time significantly. Slide 2. Shared memory computers. Shared memory computers have multiple processors accessing the same memory pool. This allows them to share data quickly without needing complex message passing protocols. Key features: 1. Single address space. All processors operate on the same memory, making data sharing easier. 2. Fast communication. Since there is no need for sending data between processes, the speed is high. 3. Synchronization mechanisms. To prevent data conflicts, shared memory systems use mechanisms like mutexes, semaphores, and locks. 4. Scalability issues. Adding too many processes can lead to memory contention, where multiple processes try to access the same data at once, slowing performance. 5. Cache coherency management. Each core has its own cache, so shared memory systems must ensure data consistency across all cores. 6. Multithreading support. Efficient multithreading allows better utilization of CPU cores. 7. Easier to program. Compared to distributed systems, shared memory programming is more intuitive because there is no need for explicit message passing. Example: Intel's Xeon processors are widely used in shared memory servers that handle multi-threaded workloads such as databases and scientific computing. Significance: shared memory systems are ideal for low latency, real-time processing where tasks need fast access to a common dataset. Slide 3. Advantages and disadvantages of shared memory systems. Shared memory computers offer fast communication and easy data sharing, but they also have scalability limitations. Advantages: 1. Fast data access, no need for explicit communication between processes. 2. Simpler programming model, easier to implement compared to distributed systems. 3. Lower latency, memory access is direct, making operations faster. 4. Efficient for small systems, works well when the number of processors is limited. 5. Direct core communication, no message passing overhead, improving efficiency. Disadvantages: 1. Scalability limits, adding more processors can lead to performance bottlenecks. 2. Memory contention, too many processors accessing the same memory slows execution. 3. Cache coherency issues, requires mechanisms to ensure all cores see the same data. 4. Expensive hardware, requires specialized high-speed memory architectures. 5. Limited distributed computing capabilities, cannot scale over multiple physical machines. Example: multi-core laptops and high-performance servers use shared memory for applications like video editing, gaming, and data analysis. Key takeaway: Shared memory systems work well for small-scale, high-speed computations, but they are not suitable for large-scale distributed computing. Slide 4. Distributed memory computers. Unlike shared memory computers, distributed memory systems consist of multiple processes, each with its own private memory. Processes communicate with each other through message passing over a network. Key features. 1. Independent memory units. Each processor operates on its own data without accessing a central memory pool. 2. Message Passing Interface (MPI), a protocol that enables data exchange between processes. 3. Higher scalability, can scale to thousands of processes across different machines. 4. Complex programming model, data must be explicitly shared between nodes, making programming more challenging. 5. Reduced memory contention, no shared memory bottlenecks. 6. High network latency, communication delays occur when exchanging data across the network. 7. Supercomputing applications, used in HPC clusters, cloud computing, and distributed databases. Example: Amazon AWS and Google Cloud use distributed memory architecture to handle large-scale applications like big data analytics and machine learning. Significance: distributed memory systems allow high scalability and are used in cloud computing, AI, and scientific simulations. However, they require careful management of data transfer and synchronization. Slide 5. Shared memory versus distributed memory systems. Understanding the differences between shared memory and distributed memory systems is essential for choosing the right architecture in high-performance computing (HPC). Let's break down the key differences. Explanation of key differences. 1. Memory model. In shared memory systems, all processors access the same memory pool, making data exchange simple and fast. In distributed memory systems, each processor has its own local memory, and data exchange happens explicitly via communication protocols. 2. Communication. Shared memory systems allow implicit communication, meaning processors access the same memory space without extra programming effort. Distributed memory systems require explicit communication through message passing mechanisms like MPI, Message Passing Interface. 3. Scalability. Shared memory is limited in scalability because too many processors accessing the same memory cause contention. Distributed memory scales much better, as each processor manages its own memory, enabling thousands of processes to work together. 4. Programming complexity. Shared memory programming is easier since processors automatically share variables. Distributed memory requires more complex programming to explicitly manage data transfer between processes. 5. Latency. Shared memory systems have low latency because data access is direct. Distributed memory introduces higher latency since processors must communicate over a network. 6. Use cases. Shared memory systems are best for small-scale multiprocessing like multi-core CPUs and single-node servers. Distributed memory systems are used for large-scale HPC clusters such as weather modeling, AI training, and cloud computing. Example: a high-performance workstation for video rendering typically uses shared memory, while a supercomputer like IBM Summit relies on distributed memory for massive simulations. Key takeaway: shared memory systems are better for fast, small-scale computations, while distributed memory systems scale well for large and complex workloads. Slide 6. Hybrid systems. Hybrid systems bring together shared memory and distributed memory architectures, offering a balance of speed, flexibility, and scalability. They are widely used in scientific simulations, AI training, and large-scale cloud computing. Explanation of key features. 1. Multi-level memory hierarchy. These systems incorporate local shared memory for fast data access and distributed memory for scalability. 2. MPI and Open integration. MPI, Message Passing Interface, is used for communication between distributed memory nodes, while Open multiprocessing, handles multithreading in shared memory. 3. Better resource utilization. workloads are distributed efficiently between processors and memory types, improving overall performance. 4. More complex to program. Since hybrid systems use two different memory models, developers must understand both shared and distributed programming techniques. 5. High efficiency for large systems. These architectures optimize computation for large-scale applications such as climate modeling and deep learning. 6. Scalable and high performance. Hybrid systems provide the best of both worlds, ensuring low latency and high computational power. 7. Customizable for workloads. Depending on computational needs, resources can be allocated dynamically. Example: IBM Summit, one of the world's fastest supercomputers, utilizes a hybrid architecture to process massive AI and scientific workloads efficiently. Key takeaway: hybrid computing is essential for modern HPC systems, offering both speed and scalability. Slide 7. Network computers. A network computer is a system where computing resources are centralized in remote servers, rather than being processed locally. These are widely used in cloud computing, business environments, and AI-driven applications. Explanation of key features. 1. Cloud-based processing. Tasks are performed on remote cloud infrastructure, reducing local processing requirements. 2. Thin clients. Devices using network computing often rely on minimal hardware, with most processing handled remotely. 3. Real-time data processing, used in big data analytics, stock trading platforms, and live AI applications that require continuous data processing. 4. Scalable computing power. Network-based systems allow on-demand scaling, ensuring efficient resource allocation. 5. Low hardware costs. Since processing is offloaded to cloud servers, companies can use affordable client devices. 6. Network dependency. These systems require a stable and fast internet connection for seamless operation. 7. Security and privacy challenges. Since data is stored and processed remotely, cybersecurity risks must be managed. Example: Google Drive and AWS Lambda are popular examples where computing tasks are offloaded to cloud-based network computers. Key takeaway: network computers reduce local hardware dependency but require strong security and stable internet. Slide 8. Advantages and disadvantages of network computers. While network computers offer scalability and efficiency, they also come with security risks and network dependency. Advantages: 1. Lower cost. Users don't need high-end local machines since processing happens on the cloud. 2. Automatic updates. Software and security patches are managed remotely, reducing maintenance efforts. 3. High scalability. Computing power can be expanded dynamically as demand increases. 4. Remote accessibility. Users can access their applications from anywhere with an internet connection. 5. Energy efficient. Cloud-based processing reduces power consumption on local devices. Disadvantages: 1. Requires internet connectivity. Performance depends on a stable and fast internet connection. 2. Data privacy risks. Sensitive data stored remotely may be vulnerable to cyber threats. 3. Latency issues. Network delays can impact real-time applications. 4. Less control. Users must rely on cloud providers for computing resources. 5. Security concerns. Cloud computing is a target for cyber attacks, requiring strong encryption and access controls. Example: Google Chromebooks function as thin clients, relying on network computing for most tasks instead of local execution. Key takeaway: network computers provide a cost-effective solution for cloud-based applications but require stable connectivity and security measures. Slide 9. Future of parallel computing. The future of parallel computing is being shaped by advancements in AI, quantum computing, and energy-efficient architectures. Key future trends. 1. Quantum computing integration. Future systems will integrate quantum processors with traditional HPC for exponential computing power. 2. AI-optimized parallel processing. Machine learning and neural networks will leverage advanced parallelism for deep learning acceleration. 3. Energy-efficient parallelism. Focus on low-power architectures to reduce energy consumption in supercomputing. 4. Advanced GPU and TPU computing. Graphical processing units (GPUs) and tensor processing units (TPUs) will enhance parallel workloads, especially for AI. 5. Scalable edge computing (HPC) will be optimized for IoT, 5G, and real-time data processing at the network edge. 6. FPGA and ASIC acceleration. Custom field programmable gate arrays (FPGAs) and application-specific integrated circuits (ASICs) will boost performance for domain-specific tasks. 7. Dynamic code adaptation. AI-powered compilers and adaptive parallelization will automatically optimize code execution based on real-time workload analysis. Example: Google's tensor processing units (TPUs) enable AI-driven applications to scale efficiently using parallelism. Key takeaway: the future of HPC will integrate AI, quantum computing, and energy-efficient parallel architectures for next-gen applications.